So last time we had a look at if x is a random variable, a discrete random variable with a binomial distribution, such as if x is a random variable with a binomial distribution, we said n is the number of Bernoulli trials, the number of trials that happens, and p is the probability of success. If that's the case, we learned that the expected value of x is np. That was intuitively obvious, but we did prove that from scratch. And we said that we wanted to look at the variance of x, and we've been told it's npq, but we'd like to have a look at proving that one. There were a couple of things that we used along the way of our proof for the expected value of x that I'd like to just remind you of, and then I'll quickly prove the variance of x is npq. So one of those things that we used along the way was the fact that nck is equal to n on k times n minus 1 c k minus 1. So that was quite a good thing to use during the proof. Another thing that we should realize is that when you add up all the probabilities, you get 1. So the sum of all the probabilities, so from k equals 0 to n, of all the nck p to the k q to the n minus k's, that should be equal to 1. Now, I keep calling it q. Q is 1 minus p, because being binomial, the probability of success is p, the probability of failure is 1 minus p, because you can only have those two options. That's why it's called a Bernoulli trial each time in this. And q is 1 minus p, but it's easier just to write q each time, but bear that in mind. All right. So when you add up all the individual probabilities, and we've expanded out the binomial so we can see that each one of them looks like that, you get 1. And we proved last time that the sum of all the xpx's, when you add up all the xpx's, that's the expected value, you get np. So the sum from k equals 0 to the n of k times nck pk q to the n minus k is equal to np, is something we've just established last time. So we use this in our proof. This idea comes up that when you add all the probabilities together, you get 1. And now we can use this as well if this comes up ever in the further proof, where the k in there is the only difference of this, but then that will equal np. So they're the main things that we needed to know before we could get started. So with that in mind, I'm going to launch into looking at the variance. Now, I'm just going to say that we're assuming that the variance of x is equal to the expected value of x squared minus the expected value of x squared. That's a commonly used formula. I don't want to derive that one now, but it's a formula that you're allowed to start with, rather than finding the sum of all the x squared px's, which you could also start with. So let's start with there. We already know that e of x is np, so I can put np in for that. Here, I'm going to have to look at the sum of all the x squared px's here. So this is the sum from k equals 0 up to n of k squared times, and px, which is these guys, nck p to the k q to the n minus k. So that's that written out, minus, and then this is np squared. And now we're going to do the same replacements that we did when we worked out the expected value. So the first thing I'm going to do is I'm going to change this guy here using this formula up here. So I'll write that down now. We've got the sum from k equals 0 to n of k squared n minus 1c. Whoop, replace it properly. It's n on k, n minus 1c k minus 1, p to the k, q to the n minus k. And of course, we've got our minus n squared p squared sitting out the end there. It'll just carry through for the whole of this. I've got room for another line here. And you would recall that the first term will be 0, because if you put 0 in for k here, 0 squared is 0. So 0 times whatever that probability is will be 0. So I can actually move this and say it's from k equals 1 up to n. So I might do that now. And at the same time, I'll cancel one of these k's here. So I've got the sum from k equals 1 up to n of kn, n minus 1, c, k minus 1, p to the k, q to the n minus k, minus n squared, p squared. Now, I guess instead of writing a whole nother line of working, I can say if I see a constant in this, this is the summation here. We've got this happening, and then we've got your minus n squared p squared just on the end, right? In this summation, this n is a constant, so it can come out the front. So I don't really need it in there. I'll just put a times, and I'll pop the n out the front of that summation. We've said this before, you can take a constant outside a summation in the same way you can take it outside an integral. All right, the next thing I'm going to do is apply that rule that I can change that to p of k minus 1 times p, so that I can get the constant p out of that as well. So I'm going to write that down up here. We've got n and k equals 1 to n of k, and then we've got n minus 1 c k minus 1 p times p to the k minus 1, so that'll get it back to p to the k, and q to the n minus k. So that's all, it's one thing here, and then minus n squared p squared is at the end there, which just gets carried through. So that's a good step, because this p in here is a constant, whereas k keeps changing, so it can't come out. But the p can come out the front as well. So this is np times the sum from k equals 1 to n of k, n minus 1 c, k minus 1, p to the k minus 1, q to the n minus k, minus n squared p squared. So we're really starting to get down to where we can start making some substitutions. And the last thing I want to do is change this, instead of n minus k, to n minus 1 minus k minus 1, so it will work out nicely. So I'll just write that here, n minus 1 minus k minus 1. If I expand that, I get n minus 1 minus k plus 1, which is n minus k, right? So instead of n minus k, I'm going to write that for the q power. So np, sum from k equals 1 to n of k, n minus 1 c k minus 1, p to the k minus 1, q to the n minus 1 minus k minus 1, and then minus n squared p squared stuck out the end there. So now we've thinned that right out, and we're going to do a substitution. So I'm going to let m equal n minus 1. I'll write that here. Let m equal n minus 1, and let r equal k minus 1. And our k used to go from 1 to n. I'll just write that here. K, it went from 1 to n. So r is going to go from, k goes from 1 to n. So 1 minus 1 to n minus 1. In other words, from 0 to n minus 1, which is m, right? So now the summation, because it's an r summation, is going from 0 to m. And if I did replace k in the summation, k is equal to r plus 1 from this. If you look at this, k equals r plus 1. So I'm going to need to erase a little bit here so that I can now do a bit more of my working. So bear with me for a tick. All right, so we're up to here where we're going to do some replacing. So we've got NP out the front of this. Then the summation is now from R equals 0 to M. And instead of K, I have to write R plus 1. And then we've got, instead of N minus 1, CK minus 1, it's just MCR. And then P to the K minus 1 is P to the R. And Q to the N minus 1 minus K minus 1 is Q to the M minus R. And then, of course, after that's done, we've got this minus n squared p squared stuck out the end, but it's not part of the whole summation thing. So this r plus 1 is multiplying this here, so we can separate those out. We've got np, and we've got the sum from r equals 0 to m of r times mcr p to the r q to the m minus r, plus the sum from r equals 0 to m of 1 times mc r p to the r q to the m minus r, and then of course our minus n squared p squared sticking out the end. So all I did there was see this r plus 1 in brackets, that's r of these plus 1 of these, so I've separated them out. I've got r of them and 1 of them there. Okay, now this should look familiar from what we did with our expected value. Now we know that the expected value, I'll just write it down in red under here, expected value of x is equal to the sum from k equals 0 up to n of k times n c k p to the k, q to the n minus k. That's what the expected value is, where you add up all the xpx's, basically. You add up all the xpx's. So that's going to be your x, and that's your p of x each time. Well, this here is looking extremely similar to this, all right? And we know that this equal to NP, because we worked it through and we got that last time. Well, this is looking very similar, but instead of K, it's got an R, and then it goes MCR, and it goes R, M minus R. So basically, wherever you see an N here, this has got an M, and whenever you see a K here, this has got an R. So this summation here, instead of being NP, it would be MP. MP. So that's what I'm going to replace that with. I'm just going to say that red stuff there is going to be MP. P. So we got NP. This red stuff is MP plus, and this is just, because there's a 1 in here, you might as well forget about that. And that's just the sum of all the probabilities, isn't it? That's each probability worked out. So that's just 1. And then minus n squared p squared. All right, I don't want that m there. What's m equal to? N minus 1. M equals n minus 1. So let's just pop that in there. N minus 1 p plus 1 minus n squared p squared. So this is NP into this stuff, n minus 1p plus 1 minus np. If I factorise np out of both this and this. So it's np, and this is np minus p plus 1 minus np. All right, so these two np's gone, and that's 1 minus p. np, 1 minus p. But we know, and we said this, I hope this is, yeah, I've got enough room on the bottom. We said this before, 1 minus p, we've been calling that Q all along. P is the probability of success, 1 minus p is the complement of it. So that's equal to NPQ. So the variance of X is NPQ.